So we have a situation like this. So we start in the small space, we go to the big space with the unbounded operator, the operator that's unbounded if we look at it as an operator here, which is bounded if we look at it into the bigger space, and then we need the preconditioner to go back. And now if we want to preserve symmetry, then we need a symmetry property of the preconditioner. It should roughly be in a way that the bilinear form generated by this operator B, and here now this is a duality pairing between the two spaces, defines an inner product on this X star space. Then you would exactly be in a situation that the composed operator B times A is symmetric. So our conclusion is then if we put on a preconditioner like this, then we can apply a method like Krylov space methods to this problem. So the situation here is slightly, even in some sense, more convincing than it is for all the discrete problems where you introduce preconditioners to have an iterative method converge fast. If you really go to the limit, to the infinite dimensional problem, you need the preconditioner to have a well-defined problem. Okay? So that's sort of what you can say. And then you can say at once, we know that when we have bounded operators, know the composition of B and A, they are bounded from X to X. So of course the Krylov space method will converge, and it would converge with the rate depending on the condition number. So in some sense, if you are there, can manage to construct this preconditioner, then it's sort of just, you leave everything just up to the iteration, which is sort of an automatic generation, and you have your solution. Okay? So this is sort of the point of view. So let's take a quick look at sort of the Bretzi theory for saddle point problems and see how that fits into here. So the Bretzi theory corresponds to you minimize a quadratic functional given linear constraint in a certain way. And many of you have seen this problem. So you have a bilinear form, you have a right-hand side, and you have an affine constraint in this way. And you know this gives you systems of this form, the typical saddle points structure, where we have this problem then posed in two spaces called V and Q here. These are sort of the typical, you have to call them something, so this is what we call them here. Here is the system again, and you know the Bretzi condition are then giving basically two conditions to show that this problem is well posed. One is a sort of insupity condition for the bilinear form V that generates the constraint, and the other is the coercivity of the bilinear form A on the kernel, on the kernel of B, of the associated bilinear form B. So that's sort of the two conditions, and what you then can say at once is that the complete coefficient operator that you get out of this system, which is an operator mapping V cross Q into its dual, and this is an isomorphism. So what this says in terms of a preconditioner is that this operator, in some sense, has the same mapping property as a diagonal operator taking V to V star and Q to Q star, such that the natural preconditioner is the one that goes the other way. So naturally you can use diagonal preconditioners because there is, what this says is that the coefficient operator, that here is not diagonal, has the same mapping property as a diagonal operator. So this is how you can say block diagonal preconditioners sort of naturally arise. So this is what I say. This operator has this mapping property, and there is a natural way of generating the preconditioner as a block diagonal guy. And you should have this now with the right positive definiteness such that they define an inner product on the dual spaces again. We're going to return to that. So let's now look at sort of well-known examples. So the first well-known example, Stokes' problem, that many people have seen before. If you look at that in a weak formulation using H1 with zero boundary condition for the vector variable and L2 with mean value 0 for the scalar, then you can have the weak formulation like this. You need, of course, the soup condition, which is not totally trivial in that case. But except for that, you can say at once, since the Bretzi conditions are known to hold here, that the coefficient operator A, that we formally can write this way, the one we define weakly, is an isomorphism going from here to here. So sort of the natural preconditioner is the one going the other way, and the natural precondition going from H minus 1 to H1 again, and from L2 to L2 looks like this. So this is sort of a canonical preconditioner. Of course, this problem might be as hard to solve maybe as the original, but what this sort of shows also is that you can, for this, instead of taking Laplace inverse here, you can use anything that has the same mapping property as the Laplace inverse. You can use any symmetric operator from H minus 1 to H01. And this analogy we then can take with us when we go to discrete problem, because sooner or later, of course, we're going to be interested in discrete problems. But we do going through this process of looking at preconditioning for the continuous problems, because this is going to give you a recipe of how to do it for the discrete problems. That's the whole idea. Okay, so the other thing you can look at is, for example, the mixed formulation of the Poisson problem, where the only difference is that for the vector variable we had minus Laplacian here in Stokes. Now we have the identity. That is sort of the difference. You can, of course, do the standard weak formulation of this using the spaces H div and L2, looking like this. And if you see what that means, you have generated a coefficient operator that takes basically H div and H0 div stands for the normal component is 0 on the boundary to its dual. You can characterize this dual, but we don't have to do it here. And of course, the obvious preconditioner then is sort of the natural operator taking this back here and this one back here. So you see the second one is the identity. The first one would be this operator here, I minus grad div inverse. So this operator I minus grad div is exactly the one you get out as the operator associated the H div inner product. So this is sort of a special operator because I minus grad div is just, this is just the identity if you apply it to a curl, but it acts as a second order operator if you apply it to a gradient. So it's sort of, it's not like the Laplacian, but it has this special property that leads to the need for so-called H div preconditioners. It sort of naturally come up in this problem. So this is what I said about its special properties. Okay. Now there is an alternative formulation for the system of the Laplace problem. That is, instead of using the vector variable in H div and the scalar variable in L2, you can sort of do the opposite thing. And this really comes from that these bilinear forms here you can either integrate by parts or not, so you get it in one way or the other. And then you can sort of see that you can look at this problem with the vector variable in L2 and the scalar variable in basically in H1 with some mean value boundary condition in a formulation like this. Actually, this is even more well known to you than the other because this is just a way of writing the standard formulation where with just one variable, but where we have introduced the u as grad p. That is sort of what you do here, or you can take a general right-hand side if you want. So this is even more well known to you. But there is an interesting observation of this. Now, if you look at the same, this is formally the same operator as where we use H div and L2. But now you can look at this as an operator from L2 to H1, and it's still an isomorphism into its dual. Okay, of course it's slightly differently formulated. It's not a, depends what you mean by it's the same operator, but formally it's the same operator. But they are totally different mapping properties. So what this means, since you have different spaces in our theory, the spaces where it's well posed generates the preconditioner. So this means you have two different preconditioners for this problem. Okay, which is formally the same operator, but you define it on different spaces. And if you look at these two preconditioners here, they're in no way similar. Okay, one has the identity down in the corner here, the other has minus Laplace inverse. This one has identity here, this has the inverse of an operator that sometimes is identity, sometimes is the inverse of an elliptic operator. So it's in some sense the same problem, the same operator in some sense, but with two different preconditioners. So this is what I said, they are not similar in any way.